In case you just don't have anything else to do on Friday night, you can be reading Stanford radionuclide data. There's all your elements. Well, the common ones that show up in, or whatever research they're doing at Stanford. So you can pick your poison, literally. Americium-241, that's always fun. Oh, just open it. Thank you. And you see the common things that you've been learning about: half-life, decay type, radiation hazard. I printed out the one in particular, iodine-131, for you because it's a little more interesting, a little more relevant in some ways. Just because the Fukushima nuclear reactor dumped a whole lot of this into the Pacific Ocean. So since the Fukushima dumped a whole lot of this into the Pacific Ocean, do we have to worry? No, because it's in Japan. No, we're not near Japan, right? Wrong. It's amazing how fast the Pacific Ocean currents take to get the stuff over here. Yeah, so it takes about 2 to 3 weeks. And
That
stuff.
is pretty fast.
What did they dump her?
No, it was 2 years ago, 2.5 years ago, Fukushima, after that big earthquake in Japan.
So it's too late now.
Oh, it's way too late, yes, I don't know, but it's just the fact that it is particularly a common byproduct of nuclear reactors, and it's commonly used, and I just thought, okay, that's kind of fun. So it's got a half-life of 8.04 days. You know what that half-life means now. If you happen to see these things later around the lab someplace, 8.04 days, what type of decay is it? Principally, it's beta decay, and then there's a series of gamma decays after that. So this iodine-131, what does it decay into? Let's see if we can do that. Iodine-131 goes by beta minus decay into what? Iodine-131. And who has any idea of what the atomic number of iodine is? Did we get it on here? 53. So it's 53 goes to beta minus. And what's left? The 131 is the easy one. I'll give that one to you.
54?
54. Right. 54 plus a minus 1 gives you 53. What is that one? 54. Xenon. Good old XE. And that xenon is probably in an excited state. Hence all the other gamma rays that come off of it. So basically when iodine-131, it does this. And this MeV, what does that look like to you?
Something mega electron volt?
Mega electron volt. What is your mega?
10 to the 10 to 6.
Are you asking or telling me? Better be telling me, because I'm asking you.
10 to the negative 6.
Flip a coin?
No, I said 10 to the
10 to the 6.
10 to the 6.
Because I'm
10 to the positive
comparing
6.
to a regular regular electron.
What does the
volt.
M stand for? Capital M.
It's like 10 to the next 6.
It's not like, it is. It is 10 to the 6th, yes.
Well, I'm just confused. I
want to make sure you're not
Then
confused.
I'll put it to the negative 6.
The mega is 10 to the positive 6.
Okay.
There is, whenever the mega shows up, yeah, it's a positive 6. All right. So yeah, that just tells you the energy of the electron. What electron? Yes, that tells you the energy of the electron. The beta particle, is this beta particle an electron or not the electron?
It is the electron.
This is the electron because it's the beta minus.
Yeah.
Hey. Might as well have a little fun with this since we're having a test on Wednesday. .806 MeV is the energy. How fast is it going? Pretty damn fast.
Really fast.
Yeah, you'll probably get some ridiculous number that doesn't make any sense, but let's try it and see what happens. Because these are very energetic. Let's see what we get. First, so tell me what that
So
speed
now
is.
what are we doing?
I'm gonna find the speed of that,
Electron.
electron. Speed, how do you find the speed?
Let's look at the formula.
Yes, let's look at the speed of the electron. Yes.
In joules, that's what I need to do. And then we use this equation.
You were ready for the test today, right? No, you put it off, right?
Exactly.
I remember doing this. Yeah. What? No.
That's how we should do it.
There we go. Copy that here. So am I right, just want to make sure, am I right in thinking that some of you had your positioning exam this morning? And some of you are having yours later on this week or something?
We all
No, we all have.
You all had it?
Yeah.
Okay, good, because it's always hard to talk to people who have an exam coming up. It's like, nobody wants to listen to you. And I have a lot of sympathy with that. I was planning on making today kind of easy, kind of relaxing. A little bit of review, a little bit of other things going on here, without trying to stress you out. So I just wanted to take a look at a few of these things.
So what's given in this case?
Oh dear,
Well, the energy is
you have
given,
energy of 0.806 MeV.
Oh.
and the mass of the electron is given.
Well,
Is EV the same as EK?
Well, this will be the energy of our electron.
Kinetic energy?
EV is not EK, but EV is just a unit of energy. EV, that's a mega electron volt. How fast is it going? And write this other stuff down. I have oops. All right, so let's see if we can just figure out how fast it's going. We got to deal with this 0.806 MeV. You might want to rewrite that as 806 keV. Now you got something that's a bit more familiar. Or you might just want to write it as 0.806 times 10 to the 6th electron volts times, 1 electron volt, 1.602 10 to the minus 19 joules. Gives us 1.29 roughly times 10 to the minus 13 joules. Hopefully you're able to get that out of it. And then you're saying the kinetic energy equals 1/2 mv squared. Therefore, V is equal to 2 times the kinetic energy divided by the mass inside the square root. And we get, what, 5.3 times 10 to the 8th. Which will seem like a very weird number to you. Why does it seem weird?
That's not the first second.
Meters per second.
It's fast. That's it on the fourth one.
Faster than a
Faster than the
photon,
speed of
yes,
light.
faster than the speed of light, yes. Which is not possible. But you didn't do anything wrong. What it is true is that this formula is not actually right. At very high energies, that formula is not correct. Einstein came along and had to fix that formula. So, our formula is not actually correct, but we're not gonna worry about it. I'll just put it down here.
Shouldn't we be using the correct formula?
Yeah, I would love to, but I think most of the people would run for the door.
Okay, there, no one is.
It's actually not that bad, but we won't do that. Yeah, we'll just make a note. We're not gonna worry about it, but I just wanted to do that calculation so you know how to do it and the number's weird. All right, back up to our data sheet. So hazard category. What hazard are they talking about? If you had to guess, having to do with radioactivity. Radioactivity absorbing the beta particle from this thing. So what are we looking at? 1 to 100 with that symbol there.
The food is,
Curie?
the activity.
It's some kind of activity. What is UCI?
Microcurie?
Yes, you'd have to interpret it as microcurie. They don't have the correct symbol font in their system, so they're using U for micro. You have to get used to that kind of thing. At 100 microcuries, this is the activity. So what does 100 microcuries translate to as a activity?
You mean we need to transfer it to?
Becquerels. Convert this becquerels, or also what I want to know is decays per second. How many decays per second are we talking about at the top of hazard category C? Where it says 100 microcuries. How many decays per second? So the micro is 10 to the negative 6.
10.
And the conversion between 1 Curie and 1 Becquerel. 3.7 times 10 to the 10. No idea why I remember that number. No one's fixing my brain for some reason. So they're saying 3.7 times 10 to the 6 decays per second is the upper range of hazard category C. Still seems like an awful lot. Are you getting that okay? Just a conversion. I just wanted to make sure you're aware of this thing as activity. Remember, when you see Curie, you're thinking some kind of activity. Some number of decays per second. Any questions on that conversion?
What's the difference between the different hazard levels? Like how is that? It says C.
Well, they're saying that sea level is a low-level hazard. I mean, that if I walked into a lab and saw something listed like that, it looks like it's sea level hazard, I would go tell my supervisor. If I walked in and saw something like A, I might hit the alarm. You know, where you really want to react. If you saw something that was fitting into this category, you want to definitely react to it. Make note of it, take proper precautions in case you run into these things.
So that level of hazard would be right at the site?
You know, if it was like in a little, I mean, these things come in just innocuous little glass jars sometimes. You see them and they look rather benign. It looks like, oh, cute little test tube. Woo. It's got an enormous amount of activity to it. But activity decreases with time because the sample is decaying. So let's just try something and see how it works. There's that radioactive decay law, which also is the same one for activity. A is equal to A naught e to the minus KT. Okay, you stumble into a lab someday, who knows why or where, and you find this. Okay, so somebody happened to leave a sample lying on the table, and this was how the activity was listed. It's 10 millicurie on September 21st. That is a year ago from today. Wanted to make the calculation relatively good. What is the activity today?
So the M in this case stands for what? Mac?
Milla,
Michael?
milli.
Millie. That's the other one.
Get it straight on your notes before Wednesday. What's the activity today? September 21st, 2015. before you actually try to calculate it, think about an 8-day half-life. Should you be worried about something a year later that's got an 8-day half-life? It's a whole lot of half-lives, so it should be a pretty small amount. But let's see what we get. Okay, we need to figure out what K is. How do we get K? Mm-hmm. ln of 1/2, and we have the number of days was 8.04, I believe. 8.04. Okay, 0.0862. And I'm working in units of inverse or reciprocal days here. Your decay constant has units of 1/time.
You don't have to go to seconds. Just leave it there.
We can leave it in days. If what?
Let's convert it to that.
Let's see, we got 100 millicurie, we got a 10 millicurie sample. 10 milli times e to the minus point. No, that's the other way. So that's the days. Now I need to multiply it by the time that's elapsed since the label. And how much time has elapsed since this thing was measured? 1 year. How many days in a year? Usually 365. You'd have to think rapidly whether I care about whether there was a leap year or not. And so if you're doing it like that, you will notice that your units cancel. And let's see what our sample looks like.
Why did we leave the Korea and Melly, we didn't change it?
We'll change it later. If this works, it may not work. Oh, okay, cool. Didn't work. So our sample now has an activity of 2.16, we'll call it millicuries. Oh, sorry. Very important step I left out there. 2.16 times 10 to the minus 13 millicuries. So our sample is not something to be worried about at that point. Like I said, Friday nights, you can pull all these data sheets off the web, have fun calculating away. So does that process make sense? Yeah, it's just kind of what we were doing, except we're doing it to activity instead of the amount. We're just doing it to the activity instead of the amount present.
What's the negative one of the D in 0.0862 days? In that answer.
D to the minus 1 is equal to 1/d, or D to the minus 1 is 1/days.
So where did the minus one come from?
Well, the days is in the denominator. That just tells you it's in the denominator. Remember how we work with exponents?
Bringing it up at the top of the big D. That's what it's there.
So if you have 2 to the minus 1 is equal to 1 over 2. That's what we're doing. When you move a number from the upstairs to the downstairs, this is 2 to the 1. It's the same thing as 2 to the minus 1. It's the same thing. We're just doing that with the units.
Professor?
Go.
Sorry, I'm getting really lost. Could you explain how do you calculate the e to the whatever that is?
You multiply the negative 0.0862 times the 365.
We do nothing with the -1.
You do nothing with the -1. That's just a unit. What you do notice is that that one cancels with that one.
So equals to, A equals to negative 0.862, right?
The exponent is, come on. let's see.
Or once you put g to the power -1 with the negative.
I'll put this. How about that? Is that a better way to work with it? If that's easier for you, by all means. I'm just trying to illustrate that these units cancel out, and this is one of the things you have to make sure happens, is that the units match.
Okay, question. Hey, is it negative or positive, the value?
This?
Uh-huh.
This is positive. There's a negative sign here. When you do the ln of 1/2, you also get another negative number. So the negatives cancel out.
Okay, but when you put it in the formula, negative 3, okay.
There we go. All right. So hopefully that makes a little more sense.
Right.
Did that clear it up for you, Taylor?
Yeah, I'm still a little bit confused on, I know the D's cancel out and you want that and everything, but like, don't you usually turn the time into seconds?
You don't have to, as long as the units disappear.
As long as the units disappear? Okay.
Yeah. That was another reason for doing this. Wanted to go back to that data sheet right quick. All right. That is another reason why I wanted to actually show you a real data sheet like you might find sitting around the lab someplace. Exposure rate at 1 centimeter from 1 millicurie is some number. Don't worry about that number. What I was more interested in is the sentence that follows it. Exposure is directly proportional to activity and inversely to the square of the distances from the materials, which is why I wanted you to be comfortable with those kind of sentences. Something is proportional to the activity, more exposure, inversely proportional to the square of the distance. You would know how to interpret that and put that into a calculation. Yes? Cool.
Both at the same time.
Both at the same time. Well, not both at the same time yet. We will be doing that. In terms of your basic safety precautions, get farther away from it. The activity, the exposure decreases as the inversely proportional to the square of the distance. That's your takeaway message from that. And then another type of equation or wording that you see come up in these kind of things is this one. The amount of lead required to reduce the exposure rate by a factor of 10, your 1/10 value, is approximately 1 centimeter, 1.1 centimeters. So you got a, what, almost a 3/8 inch thick lead shield will reduce your exposure by a factor of 10. It's important. And it's why you'll always find wherever they're doing nuclear medicine, lots of lead shielding bricks. And I do mean bricks. They're like bricks and sheets of lead. All right. And then of course you get all your kind of fun stuff. Hazards if internally deposited. Mix your iodine 131 into your power drink. And you get all kinds of fun things happening to you. Anyway, I'll let you read that and think about, okay. And these sort of basic ideas. These things are kind of fun to read. Arrange for a thyroid survey because iodine 131 shows up in the thyroid. So you arrange for a thyroid survey. In case you're exposed. All right. Yes. Here, let's see what we can do with that one. All right.
GM1 stands for what?
Geiger counter. Something that ticks when a radioactive source is around it. Yeah. All right. So that's what I'm thinking of. That sentence is telling me. Exposure is directly proportional to the activity and inversely proportional to the square of the distance from the materials. See if you can deal with this one for me. So at a distance of 1 meter from the source, your exposure is E1. You're only 1 meter away. How far away would you have to move from this source to get your exposure down to 1/10 of that? 10%. Trying to say the same thing with both these, they just worded it different ways in case you wanted to see how it might get worded in different ways. No one is volunteering an answer yet.
One second.
1 second, yes. Well, let's deal with the 1 over square. We'll say E1 over E2. This is what I would be thinking about. It's x1 squared over x2 squared, inversely proportional to the square of the distance.
finding E2, right?
We're finding, actually, no, we're finding X2.
Oh.
Yeah.
So E2 would be what in this case, 0.1,
E2 is 0.1 E1.
and E1 is 1 meter, right?
E1 is something we don't know. Oh dear.
Now we confused.
Well, let's just have a little faith, you know.
That's what I'm trying to figure out.
Yeah. 0.1 E1, look at that.
Is this inversely proportional?
Inversely
The X
Yeah.
square, X, the second X will be above and.
Yep, I wrote it wrong.
I was like, shit, I don't know what I'm doing.
So it's the 2 there, 1 there, very easy mistakes to make. 1 squared, x2 squared. Can you solve that for x2? Notice what happens with your E1s.
They can,
They cancel. See, we don't need to know what E1 is.
so 1 over.
Well, we're gonna solve that for x2, so it's 1 divided by 0.1 inside a square root. .16. Moral of the story, you can reduce your exposure by 10% by just backing up 3.16 meters, actually 2.16 meters. So here's our hot little source that's decaying. Here is 1 meter, and here's E1. Here is E2, which is equal to 0.1 E1. This is 3.16 meters. So all you had to do is step back 2.16 meters, basically 6-7 feet, and you've reduced your exposure by 90%. Distance is important. Anything radioactive, any ionizing radiation, distance is important.
So the answer is 2.16?
No, this is the answer to the question.
Oh, okay.
I was just interpreting the answer a little bit. We reduced our exposure significantly by moving back 2 meters and change. All right. How are we doing with this inverse, or these proportionality equations? Can you get them?
Yeah.
Yeah. Exponentials, you've gotten down pat, I think you're all set. Finishing off chapter 2. So we're going back to this idea. We've got a nucleus, and we've got some electrons in orbit around the nucleus. Not really. But we're talking about the electrons that are kind of around the nucleus. They're not really in orbits, but we'll let that go. And we're gonna stylize our picture even more. And we're gonna make it look even more like orbits. Though they're not orbits. This is our nucleus. And this is the N equals 1 shell. And this is the N equals 2 shell, and the N equals 3 shell. Such a nice naming system. 1, 2, 3 for our N. Too bad we don't keep it. Okay, N equals 1 is known as the K shell. Capital K. N equals 2 is known as the L shell. These are capitals. N equals 3 is the capital M shell. See, we just don't have enough characters in the English. Because now we're using capital M not as mega, but as the M shell. KLM, Dutch Airlines? No? It's whoever was doing the investigations back in the 1800s. I don't remember their 3 names. But after M, it's simple. Because what they did is they just went alphabetically after that. N, O, P. N equals 6. So we're just talking about our shells, our electron shells. Okay, the K shell, the N equals 1 is always the innermost shell. Some atoms don't have too many shells. Some atoms have a lot of shells. What's the simplest atom that you have in mind?
Hydrogen.
Hydrogen. Let's take a look at hydrogen. There's our hydrogen nucleus. And there's our single hydrogen electron. And if we only have 1 electron, and we know that the hydrogen is in its ground state, what shell must that electron be in? K shell. Yes, that's the K shell for the electron. What's the next element after hydrogen? Helium. Let's try helium. How many electrons does helium have?
2.
2. Okay. And our 2 electrons happen to both be in the K shell. Also in the K shell.